All right, Margaret, I'm calling this Chapter 5, Part 3, and we're going to do a calorimetry problem. This is a coffee cup calorimeter. Unlike the previous problem, where you took a piece of metal and water, we're going to do a reaction. And we're going to figure out how much heat energy the solution absorbed, and separately, we need to find the delta H of the reaction. These are two very different questions, but they are, of course, related. Look at the plan here. Maybe I should have read the question first. So here we have 50 mils of 0.500 molar sodium hydroxide. It starts out at 25 degrees. And 25 mils of 0.500 molar HCl, also at 25 degrees. After stirring, the final temperature is 27.21. What this is saying is that there's essentially heat flowing from the reaction to the solution. And so it shouldn't shock you that the Q of the solution is going to be a positive number, because basically we saw the thermometer temperature rise. Up here, the Q of the solution, all I need to do is find out the mass of the solution, the specific heat of solution, and the change in the temperature. So this first part is going to be pretty straightforward. All I'm going to do is take 75 grams of solution. How did I get that? Well, I had 25 mils and 50 mils of my two liquids, and I was told the very helpful fact that 1 gram per mil means that I have 75 grams. We're going to assume that the specific heat capacity is the same as that of water, and then the simple delta T is 2.21. I just subtracted the two temperatures. It's going to give me 693 joules. That's the Q of the solution. That's how much energy the solution absorbed. The delta H of reaction is more work, and for that I will look at another slide. What the heck did I do? How did they get a different number? 75 times 2.21 times 4.184. Oh. All right. Whoops, look at this. I already did that for you on the previous slide. To find the delta H of reaction, we need a balanced equation, and we need to know how much of these chemicals reacted, because basically it's a limiting reactant problem. We're going to have two different amounts. So this is what we did. I took my 25 mils of hydrochloric acid and my 50 mils of NaOH, and I determined how much product they each made. So this is something you did on, I think, your first exam, where you did a stoichiometry problem. You used a balanced reaction to determine how much product. It's the one that makes the least product indicates the limiting reactant. Okay? And so since that's the case, and this reaction is a very, very straightforward 1-to-1-to-1 reaction, because I created this many moles of water, that's exactly how many moles of reaction I get it. So HCl is limiting. The amount of water formed is 0.0125 moles. Since there is 1 mole of water in the balanced reaction, 0.0125 moles of reaction occurs. And so look what I did. I took the Q of my solution, flipped the sign, because that's the Q of the reaction. Remember this. Q of reaction is negative Q of solution. This was a positive number, and the energy came from the reaction, so that's why this negative is there. If I take the Q of the reaction, divide by the moles of reaction, change to kilojoules, I get minus 55.4 kilojoules per mole of reaction. So that's a limiting reagent problem in a coffee cup calorimeter. I mentioned on the phone to you that sometimes you have to use a bomb calorimeter. Why do you use a bomb calorimeter? Write that question here, and I'll write the answer. This device is used to measure the energy transfer when a reaction does produce gas phase products. For example, combustions are important if you're studying fuels or foods. Food, of course, is a biological fuel if you think about it. Because the fixed volume, basically this is a metal-walled container, it's very, very solid. It prevents any energy transfer in the form of work. Any energy that's transferred is going to be in the form of heat. Here, you have to read the problem carefully in order to determine if you can combine the water and the bomb together or if you need to calculate their values individually. What I mean by that is that in this case, the Q of the surroundings in some problems is the Q of the water, which is what this thing is sitting under, plus the Q of the bomb, or sometimes they'll just say, oh, the whole bomb is including the water. So you have to read it carefully. So let's see what the next problem is. A manufacturer claims that its new dessert has fewer than 10 calories per serving. I had mentioned to you earlier that capital C calories are equivalent to a kilocalorie, or 1,000 calories. To test the claim, the chemist places one serving in the bomb calorimeter and burns it in O2. The initial temperature is 21.862. The final temperature is 26.799. Delta T, then, is equal to the difference. I get 4.937 degrees Celsius. If the heat capacity of the calorimeter is 8.151 kilojoules per K, is the manufacturer's claim correct? So notice why they did that there. They said the calorimeter. That seems to include the H2O. They did not mention mass of the water. So the Q of the calorimeter, or you could say the Q of the bomb, is this number, the 8.151 kilojoules per K. Now remember again, delta C doesn't matter because it's a change. If I multiply by 4.937 K, I get 40.24 kilojoules. That's absorbed by the calorimeter. So that's the Q of the calorimeter. The Q of the reaction is negative 40.24. Okay? So, let's take a look at the next one. The 40.24, notice that the units were kilojoules. When converted to kilocalories, that's 9.63 kilocalories. So the manufacturer's claim is true. The heat produced is less than 10 calories for one serving. A thermochemical equation is a balanced equation that includes a delta H of reaction. The sign of delta H indicates whether it's exo or endothermic. The magnitude of delta H is proportional to the amount of substance. So what that means is in the same way that you could connect the amount of substance A to the amount of substance B using a balanced reaction, you could connect a delta H to an amount of substance by using the delta H. Really. So what we're saying here is, this is kind of all messed up above, if you have this reaction, and I say that the delta H of this reaction is equal to positive 1676 kilojoules, I could use this as a conversion factor for any amount of these things. So if I wanted to react, 1.5 moles of Al2O3, well, I have a conversion factor because 1 mole is equivalent to this much energy. And so I could use that as a conversion factor. So that's what, the question here was, let's say I had 1,000 kilojoules, how much aluminum can I react? Well, the conversion is 2 moles of aluminum corresponds to 1676 kilojoules, and since the molecular weight of the aluminum is this, essentially this is saying that if I had this much energy, can produce this much aluminum. And it's all based on the fact that when you write the balance reaction with energy, you have yet a new kind of conversion factor.